Hello and welcome back. We are going to continue talking about limits, but we are going to talk about limits algebraically. And you can think of this as the black hole situations. And a lot of that happens when we have a rational function and the denominator is 0, or when we have a square root, which we can't be less than 0, or also if we are dealing with logs. Now, just as we've done in previous videos, we are going to start with some investigation. So what I would like you to do at this point is pause the video and do problems 1 through 5. So we're going to experience the problems. It doesn't have to be formal. And then we'll come back and add some math notes and math notation. So this is a great place to pause the video. I hope you were able to take some time just to investigate and experience these problems so now we could talk about them. All right, we will go through them now, adding some math notation. The first problem gives us a function g of x and says to evaluate the limit as x approaches 0. Now for this one, we could just go ahead and plug 0 right into that equation. And once we do all the calculations, we find that the limit as we approach 0 is going to be -1/2. This is called direct substitution. And we can do that because the function exists at g of 0. So that is one method to solving limits. Now, let's go ahead and look at a graph of this function. I did this in Desmos because it shows up easier when I'm recording videos, but you could do it on your graphing calculator. And you'll notice a couple things going on. It looks like we have some sort of vertical asymptote here at x equals -2. And then another thing that doesn't show up as well on this graph, but if I hover over, you'll see that if I get to x equals 4, the output value says undefined. Now, I did draw a sketch of it here. There is a vertical asymptote here at x equals -2. And then I did draw an open circle here at x equals 4. Now, let's talk about what is going on at x equals 4 right here. And 2a says, does g of 4 exist? And the answer is no, because when I plug 4 in, I get 0 in the denominator. And we cannot have a denominator that's equal to 0. The function is undefined at that point. But problem B is saying, does the limit exist? Well, let's go ahead and trace the function from the left. As we come in from the left, we do see that we can find the limit as we come in from the left. We also can find an output value as we come in from the right. And to evaluate that, we just tried some values on the left. So 3.99, 3.999, and then some values from the right, 4.001, 4.01. And you'll see that these values are approaching 0.5. So let's go ahead and add some math notation for these values. This is going to be the limit as x approaches 4 from the left of g of x, and that's going to be 0.5. But also as we come in from the right, the limit as x approaches 4 from the right of g of x, that is going to equal 0.5. And because these agree, we can say that the limit as x approaches 4 of g of x is going to equal 0.5. So even though the function does not exist, the limit does exist. So that's where we get our answer for problem D. Now let's look at g of -2. Does g of -2 exist? And the answer is no, because we have 0 in the denominator again. We could see this defined on the graph because at x equals -2, we have a vertical asymptote. Let's look at the limits of g of x as x approaches -2. As we come in from the left, approaching -2, we see that the limit goes to infinity. So the limit as x approaches -2 from the left of g of x, this is going to equal infinity. Now, let's look what happens as we approach -2 from the right. I'm coming in from the right, and I see as I get closer and closer to -2 that the limit will approach negative infinity. So the limit as x approaches 2 from the right of g of x is going to equal negative infinity. In problem 2, the limit from the left and right matched, but now they don't match. So what do? Well, we say that the limit as x approaches -2, oops, it looks like I wrote this wrong up here, -2 from the right. So the limit as x approaches -2 of g of x, this is going to be does not exist. And I'll write it over here on the graph. The limit does not exist. And that is because the left and the right are not in agreement. All right, now question 5 says, are there any clues in the equation that help us evaluate these limits? We have our function g of x, and I just wrote it down here so we could see it. And then I factored it. And just a quick note that we are going to do a lot of factoring in this course. So if you're feeling a little weak on your factoring skills, that's totally okay. You have lots of options. There's resources in your book. There's resources online. You can contact me, and I'll be happy to direct you to some other places to work on your factoring. So we're going to factor, and then we're going to simplify. Well, when we simplify, we're going to divide out common factors. This x minus 4 is a common factor. And you'll see that's exactly where we had a hole on the graph. So a hole at x equals 4. You'll notice on the graph that we have a vertical asymptote at x equals -2. So if I set this x plus 2 equal to 0 and I solve for x, I get x equals -2. That is our vertical asymptote at x equals -2. So whatever factors divide out, that is where we will see a hole. And whatever value in the denominator makes the denominator 0, that's where we're going to have an asymptote. All right, we've experienced a problem. We've added some math notation, and now we're going to formalize it into a notes section. If we have h of x equals f of x over g of x, we have a rational function. So that's like a fraction where there's a function in the numerator and a function in the denominator. There's 4 different things that can occur. The first one is if we plug in some value for x, so we'll just say a, and it is not a 0 for the numerator nor the denominator, then the limit as x approaches a of our function is just going to be h of a. This is direct substitution. That is what we did on problem 1. Then another option would be if we have a value for x, we'll call our value a, and it is a 0 of just the numerator, not the denominator, then this is an x-intercept. So we'll say that the limit as x approaches a of h of x, this will equal 0. We did not have an example of that on the first page, but we will in the problems to come. All right, the third thing is if our value of x that we'll call a. If x equals a is a 0 of the denominator but not the numerator, then we have a vertical asymptote, and we say that the limit as x approaches a for our function is going to be does not exist because h of x goes to positive or negative infinity depending on the problem. Okay, it looks like I forgot something on option 2. This is, it will have an x-intercept at x equals a. Okay, that looks better. Okay, then the fourth scenario that can happen is when we have our value x equals a is a 0 of the numerator and the denominator, then we have a hole at x equals a. This is what happened in problem 2, but we didn't see the reasoning for it until we got to problem 5, and we could see that our zeros of x minus 4 divide out. Then the limit as x approaches a of h of x exists. All right, and to find the limit, what we're going to do is we'll substitute x equals a into the simplified function after dividing to find the limit. This is really going to be the y-coordinate of the whole. Now, one thing I forgot to say is that if you are using Pearson, they call this the theorem on limits of rational functions. Okay, one last thing on evaluating rational functions. For any value k that's not equal to 0, when you plug it into a rational function, if you have k over something approaching 0, this is going to be infinity, or if k is negative, it'll be negative infinity. If you have 0 over k, that's just equal to 0. A good way of thinking of this one is, let's say that your family orders a pizza. You come home from work, you go over to the pizza box, you open it up, and there's 0 out of k slices left. That's 0 pizza. There's nothing left for you. Then the other thing to remember is k over infinity is 0. So think of k as a constant, 1 or 10 or 20, and infinity is a giant number. If you take that number 20 and divide it by a million or a billion or a trillion or so on, that's essentially going to be 0. Now stay tuned. In the next video, we're going to do an example of each type of this problem.